Our first speaker of the session is Andy Connolly from eScience Institute. He will be remotely presenting about scaling science in the era of survey astronomy.
Okay, thank you. It's a pleasure to be here, even if it is virtual and 1 a.m. on the west coast of the US. I guess being an astronomer, I shouldn't really be complaining about that. My name's Andy Connolly. I'm a professor in the Department of Astronomy at the University of Washington. I'm a member of the Dirac Institute, which is an astronomical data science institute housed at UW. And I'm also director of the eScience Institute. So the eScience Institute oversees the data science research and education at the university. So what I'm going to talk about today is about the scaling of science in the era of big data, and in particular, some of the challenges and the opportunities that we face with experiments such as the Rubin Observatory, which will be undertaking the Legacy Survey of Space and Time, or the LSST, and data sets that will come from experiments like the Square Kilometre Array. And this is really just to name two of the many experiments that will come online this decade and represents a many billion-dollar investment in survey astronomy. So first, I wanted to note that astronomy has always been a big data science, whether we're talking about the digitization of photographic plates using a 200 megahertz Pentium Pro computer to create a terapixel image of the southern sky, or whether it's the 250,000 lines of code that were written in the early 2000s to process the SDSS data to produce the first large linear survey of the Northern Hemisphere. The challenge in those days was the lack of computational resources, both in terms of CPUs, the numbers of CPUs, and the memory that was accessible through those CPUs. With cloud computing today, we're not really in the same position, at least for optical surveys such as the LSST. The data volumes of the LSST are small relative to the data volumes analyzed by the tech companies, and even small relative to the data coming from the biology and the earth science communities. Where we do face a challenge is in how easy it is for a researcher to make use of the data and the associated computational resources. So this is a really very broad field. So what am I not going to talk about? Well, I'm not going to talk about the data reduction frameworks that are being built to process Rubin and SKA data. We build experiments with the compute resources necessary to process the data and the teams to build, test, and validate the software. Instead, I'm going to focus on how we can go from calibrated images and catalogs to the science. And that's not usually a place where we invest resources until the data have actually been taken. Often when we discuss large data sets, we talk about it in terms of the 5 Vs: the volume, the amount of data we're collecting and processing; the velocity, the rate at which we're collecting data, or the rate at which we serve those data to the community, such as the 12 million alerts we expect to generate per night with the LSST. We then complain about the variety of the data, meaning the data complexity, as we work with structured data, for example, tables of features, or unstructured data like light curves with varying numbers of observations and temporal sampling. And we also complain a lot about the veracity of the data, or the noise, or the calibration of the data. But I think in many ways we ignore the final V, the value or the information contained within the data. And what I want to talk about over the next 20 minutes or so is, if we think about the structure of the data and the physics of the problems we're trying to address, or the questions we're trying to answer, we can often reduce the complexity of the analysis that we want to undertake. This leads to a reduction in the computational resources needed, and also opens up the types of analysis frameworks that we can utilize. So by simplifying the data, or how we can efficiently represent or model it, which in itself requires a detailed understanding of the noise, we can begin to develop analysis tools that may be computationally tractable and usable by the majority of researchers, not just those with excellent coding abilities. So I'm going to illustrate this point with a couple of examples coming out of the work from the Dirac Institute at UW. On the left, you can see the distribution of outer solar system asteroids, or trans-Neptunian objects, or TNOs. And I'm showing them as a function of their perihelion distance and eccentricity of their orbit. There are about 2,000 known TNOs in the solar system today. The positions and the orbits of the TNOs trace the history of the solar system. As the giant planets migrated from the inner solar system outward, in doing so, they interact gravitationally with the planetesimals, or the asteroids, and scatter them into the outer solar system. The properties of the planetesimals, for example, the number of binary asteroids tells us about how dynamically hot this process was. The more dynamical the process, the fewer large separation binary asteroids are going to remain. So tracing the properties of the TNOs allows us to map the history of the planet, of the planetary migration, to see if there are other belts of asteroids beyond the Kuiper belt, to search for evidence for other large bodies in the outer solar system, for example, the Planet 9 searches, and potentially even to probe the properties of the primordial material from the Oort cloud. Traditional approaches for finding TNOs are to identify moving sources in individual images, as we can see on the right-hand side. In the real world, we don't have red circles on the sky to identify where the asteroids are, but the algorithms for tracking these slowly moving objects, and they're moving at about 1 arc-minute a day, the algorithms for tracking them are well known. And so LSST, using these algorithms, will detect about 20,000 TNOs over the period of 10 years. And this will increase the number of known TNOs by about a factor of 10. These algorithms, however, rely on the detection of an object in an individual image. So the searches are limited to the depth of a single LSST image, or about an AB magnitude of about 24.7. If, however, we knew the trajectory of the source ahead of time, we could shift the images to account for the motion of the asteroid and co-add the images to detect the asteroid at high signal to noise. And this is known as digital synthetic tracking. Unfortunately, we don't know the trajectories a priori, so we have to undertake many, and by which I mean billions, of blind searches, evaluating many candidate trajectories to look for evidence for a source. And this is really computationally expensive, and so it's generally only been undertaken for very small areas of the sky. But more recently, Peter Whittam and collaborators showed that if we pre-convolve an image with a PSF, we produce a likelihood image, where the value of the likelihood image at a given position just tells you the probability of a point source existing at that point. So now we can determine the likelihood of a point source being represented in a stack of images simply by summing up the log of the likelihoods. To search for moving sources, we can take an arbitrary trajectory and we can sum the log likelihood at the relevant positions in the stack of images. So we never have to get to a point where we shift and stack the images themselves. This maps very naturally onto processors such as GPUs with CUDA, where each potential trajectory that we want to search is an independent evaluation of a set of pointers within an image or within a set of images. So transitioning from a CPU to a GPU enables billions of trajectories to actually be evaluated. So we can evaluate about 1 billion trajectories for 15 4K by 4 images within about a minute. And if we couple this with a convolution neural network to remove some of the false positives, I don't really have time to go into the details about that, but I'm happy to talk about that later. We end up with a fast detection method for detecting our asteroids that are well below the detection threshold of a single image. So the right figure here shows the results of such an algorithm applied to a set of DECCAM data taken with a 4 meter at CTIO. The first dashed line that you see is the detection threshold of a single image. So that goes down to about 23.1 magnitudes. The second dot dashed line that you can see is the theoretically co-added depth, going down to about 10 sigma if we stacked all of the images, and this goes to about 24.5 magnitudes. The completeness of the detected asteroids using the algorithm I just talked about is shown by the blue histogram and is within about 1/4 of a magnitude of the theoretical limit of the data. So taking this approach, applying GPUs, we're pushing the detection threshold about 1.5 magnitudes deeper than the traditional approach for detecting TNOs in single images. And so the power of this is that a single transformation into a likelihood image simplified how we could search for moving sources. And the left figure, you can see an example of one of the detected TNOs. And this is from 20 individual postage stamps went into this detection. The co-added image only has a signal to noise of about 15, but the postage stamps that went into the detection of this track have detections at about 3 sigma or less. If we want to take these sorts of techniques and we want to apply them to the LSST survey, even if we're working with just 30 days of observations, this comes with a lot of computational challenges. The longer the baseline for the search, the more area we have to search. The larger the area that we search, the more efficiently we must cache images into the GPU. This is all computationally tractable. Mario Juric estimated that it would take about 10 million GPU hours to go out about 30 days worth of LSST data. So this is expensive but possible. But more challenging is that the trajectories of the asteroids, even in the outer solar system, are not going to be linear. So while the algorithms that we use assume linearity, the reflex motion of the Earth adds curvature, so the prograde and retrograde motion, and it adds curvature to these tracks. And so for 30 days of data from the LSST, this will create nonlinearities up to about 30 arc seconds. So naively, if we take the approaches that I've talked about before, this would increase the computational resources required by about 60-fold, because we need to be able to search our searches to be within about half a PSF, the true trajectory, in order to detect an object. This really makes this project essentially computationally impossible, at least from a cost perspective. But again, if we think about the structure of the data and the model that we're fitting, we can recognize that the complex orbits that we see in the figure on the left, due to the fact that we observe these asteroids in the topocentric space, we're observing from the Earth, so we see the curvature due to the prograde and retrograde motion. If we project into a heliocentric space, reference to the sun, and assume a distance to the asteroid, the orbits become elliptical and they linearize on the sky with curvatures of less than about 1 arc second. And you can see this on the right side of the figure. So we know the position of the Earth. We know the position of the Earth at the time of the observations. So we can correct for this in the searches and reduce the computational complexity of the search by almost 2 orders of magnitude. And the impact of this, just with a single data transformation, is that it simplifies the computational model. It simplifies it sufficiently that TNO searches with the LSST could increase the depth of the detected TNOs from a single image of about 24.7 magnitudes down to about 30 days worth of co-added data. So now we're getting down to about 26.1 magnitudes. This would enable us to detect about 8 times more TNOs than we thought possible, detect minor planets such as Sedna out to about 300 AU, and possibly even probing objects that's originated within the inner Oort cloud. And all of this without taking any additional data. So what I'm trying to show is that if we use our understanding of the physics, moving beyond what has been common today, where we take these data-driven discovery approaches, if we take more of a physics-driven discovery approach, this has a real impact on the computational complexity needed to get to the science. And this is true for classification, and it's true for the other end of the distance scale. For example, using supernova cosmology, where we want to estimate the distances to a sample of type 1a supernovae. So one of the primary limitations on supernova cosmology is accurate typing of the supernovae. Usually we do this by taking a spectrum of the supernova close in time to its explosion. But if we could classify type 1a supernova just from their light curves, we wouldn't need the spectroscopic confirmation. And that would reduce the amount of follow-up spectroscopy using 10-meter class telescopes. And also it would increase the size of the samples of supernovae that we can use in our cosmological studies. We can always get the redshift to the supernova from the host galaxy, and we can do that after the supernova has faded. And because of this, there's been a lot of work on the development of autoencoders and neural networks. And there's been significant advances in how we apply these autoencoders and neural networks to the classification of light curves. And examples of this are shown here with the SuperRain model from Ashley Villar and the collaborators. There are other examples such as the avocado model from Kyle Boone that won the plastic challenge. And together, these different models are achieving about 75% efficiency in identifying type 1a supernovae from samples of transient sources or transient light curves. And this is 75% using not simulated data, but from real data such as pan-stars data. Most of these approaches are as you can see from this example with the SuperRay model, take as input the light curves or fluxes from the supernova and they learn a model that tries to explain how the light curve varies as a function of supernova type, or as a filter, or as a function of redshift, or as a function of observing time. However, as Carl Boone at Dirac noticed, if we can separate the intrinsic unknowns or the latent variables, for example, the variables that represent the variation in the spectroscopic or the spectral properties of the supernova, we can separate these from the physics that we do know. And the physics we know is the redshift, the filter curves, the host galaxy, the dust or obscuration, and the observing time. If we separate the intrinsic unknowns from the known variables, this reduces the dimensionality of the complexity of the models needed to classify the supernova. So the right-hand side of this figure shows you the latent space of the supernova spectra for different types of transient and variable sources. And this can be represented just by a handful of dimensions or components. So learning just the intrinsic properties of the sources also reduces the need for the training data to be completely balanced or representative. And it also enables us to naturally incorporate additional observations, for example, those taken at different wavelengths. And the performance of this physics-based approach using benchmark data from the plastic data challenge is shown on the left-hand side. I'm sorry, I'm being told I'm out of time, but I think this is a 30-minute talk. And so let me just, so the performance of this physics approach using the benchmark data from the plastic data challenge shown on the left. In the orange, we show the avocado model. And this was a model that won the plastic challenge, the supernova classification challenge, winning from about over 1,300 entrants. In the blue, we show the results from this new physics-based approach, and we call this ParsNet. It's important to note that this physics-based approach isn't really an advance in the complexity of the neural network architecture. It comes from more of a careful separation of what we know and what we want to learn. And this figure shows on the left-hand side the completeness of identifying type 1a supernova from a mixed sample of variable sources, where we set the threshold so we'll allow 10% contamination rate. Separating the physics from the intrinsic properties improves the supernova completeness by 10% over at the avocado approach at a redshift of 0.4. And by the time you get out to a redshift of 1, the improvement is about 50%. If we take a fairer comparison where we don't adopt the data augmentation techniques that were used by avocado, and we show this in the central figure, then the improvement is substantially better. By a redshift of a half, we're about a factor of 2 better than the traditional approaches. If we continue our focus on information, simplicity, and reducing the computational resources, we can consider how these physics-based approaches, opposed to purely data-driven approaches, might impact the analysis frameworks we want to build to deliver the science for the LSST data. One of the questions we're trying to address at UW at the moment is how we should really invest in software for science development. Do we build large, scalable infrastructures that try to meet a large swath of the science needs of the community? Such a system would likely take longer to develop. It would be higher in cost, but it has the potential to really multiplex the amount of science that you can extract from these systems. This has not been a particularly successful approach in other fields, such as computational biology, where frameworks have been developed over multiple years, requiring millions of dollars of development. And by the time they were released to the community, the field had really moved on. And so alternatively, perhaps we could be creating simplified structures, running bespoke analyses for specific science questions. This would be naturally more agile, more rapid development, but the applications, the science that would come out would be limited. So one of the questions we've been trying to think about at UW is there a middle ground? And one of the things we're finding is that if we can reduce the size of the training samples, if we can reduce the complexity of the data models, as well as the simplification of how we want to parallelize our approaches to large data sets. For example, can each source or light curve or track be analyzed independently? If we can then simplify the models, it opens up our analysis that we want to run to a much broader range of computational tools. And this ranges from the serverless approaches such as CloudNot and LithOps, These essentially take Python functions, containerize them, and allow them to work on cloud services, or whether we use the more traditional parallel analytics frameworks such as Spark and Dask and Ray. And this isn't really to say that you can't run complex workflows on Spark or Dask or Ray, but debugging of these systems is a real challenge, especially when memory usage is high. So instead, if we can keep the analysis simple, if we can keep the memory footprint small, we can work on extending these existing frameworks to meet the needs of the astronomers. An example of this approach is the Axis, or Astronomy extensions for Spark, which extends Spark with a data partitioning scheme that's appropriate for sources distributed on the sky. It adds in a sort, merge, join optimization for cross-matching large astronomical catalogs. And it also enables efficient Parquet file access to light curves, accessing the ZTF data. Spark provides a simple interface for writing user-defined functions, integrating Spark with the ZTF light curves with a data structure that maps to the astronomical objects. So rather than working with tables of observations, we can work efficiently directly with an object that corresponds to a light curve. And this allows us to rapidly and efficiently search through ZTF light curves and look for unusual sources. And in this case, I'm going to show you an example where we were searching through 1.5 billion ZTF light curves. And what we wanted to do is to identify unusual objects, counterparts to Boyajian star. So Boyajian star, or Tabby star, is a highly variable and unusual main sequence star. It was found in the Kepler data, and it was found many years after the data were actually taken. So using Axis on Spark, it took about 450 core hours, or about 2 hours of running on a cloud resource in terms of clock time. And it took about 450 core hours to process about 1.5 billion light curves. And it did this to identify periods of dimming within the light curve that looked like the variability that we were finding in Boyajian stars. And these are broad dips in the light curve lasting multiple days. It then took us about 10 hours to save the results to disk, which is a different story. But because the analysis was simple, because it had a small memory footprint, it was easy to run. And this was critical because the science workflow turned out to be very iterative. Identify an unusual set of light curves, correlate with known features or bugs in the processing, filter out the unphysical results, and repeat until the astronomical sources were left. Keeping the memory footprint low meant that we didn't have to spend a large amount of time debugging Spark, which, as many of you know, can become a challenge because you rapidly end up working trying to debug Scala at the bottom end. You can see some of the results of this work on the right-hand side, which shows you some of the 11 Boyajian star counterparts that we actually found in the 1.4 billion light curve. So this is really spending 2 hours of compute time on a cloud resource, but not 2 hours of work to find a 1 in 100 million event. And so as we developed the Boyajian star, what we began to realize that debugging, even though the debugging was limited, having people who knew how to write and who developed the system, having them available to support the work that we did really accelerated the discovery process. And this really isn't restricted to astronomy. In a survey of about 330 PIs at UW, one of the problems that was mentioned was the lack of access to software engineering to build robust and maintainable code. It wasn't access to the actual funds, it was access to the actual engineers to do the work. And so this has actually led to a new initiative that's just started up to support the science for LSST. It's called the LINK Frameworks, which is a program housed at CMU and the University of Washington, supported by the Schmidt Futures Foundation. LINK's goal is to build on what we've learned in developing scalable analysis tools. And initially, we're going to be developing algorithms to support solar system science, time series analysis, and photometric redshift estimation. And our goal is really to use professional software engineering examples, bringing in experienced industry-trained software engineers to develop open source tools. And so as a somewhat of a shameless plug, if you're interested in working on building these tools to make science discoveries with LSST, I'd be very happy to talk to you. So we are actually hiring. So as I'm coming to the end of my time, let me wrap up by just saying that it's not really the volume of data that's really driving the challenges in astronomy, it's the complexity of the science. So when we spoke with the science collaborations working with Rubin data, they identified a number of science cases that they wanted to work through in the first year of operation, requiring about 100,000 to 3 million CPU hours. If we could focus on the physics of these questions, we might be able to reduce the computational needs. It's not just really about the hardware. The tools don't always exist, even industry tools that are robust enough to scale to a typical science analysis. And this means that we need to be able to extend these open source packages, whether it's Spark or Dask or Ray, to work with astronomical questions or to address the astronomical questions. Extending existing software, whether it's industry or academic, requires significant software engineering skills and isn't really the job for a typical graduate student. The access extensions that I talked about earlier in this talk still haven't been integrated into the Smart Master because it takes time and resources to upstream changes into the underlying code base. And so we're still in the position where we're supporting a branch of the code. But I think there's a real opportunity to identify what are the needs in terms of developing and extending the software tools. And can we actually build a roadmap for the science software infrastructure? And can we actually build this across multiple astronomy science experiments and potentially across different scientific fields? And by doing this, we might be able to bring together some of the software engineering support that we need to extend these open source packages and to make them useful for the science that we want to do. And so I'll thank you for your time, and I'm happy to take questions. And if you don't have questions, I'll leave this contact information up if you're interested in working on the Linked Frameworks project. Thank you.
Okay, thank you, Andy, for the interesting talk. Any questions from the audience? Okay, there's a couple of questions on Discord. One question by Michelle. She asked, do you have any thoughts about how these techniques can be adapted for real-time classification, which is, of course, what we really need to optimize spectral follow-up?
So I think one of the really interesting aspects about the Parsnip work, the classification of the light curves, is that it appears to work well for early observations of light curves. And it also comes with a probabilistic classification or a probabilistic representation of the light curve itself. So I think we can begin to integrate these sorts of tools. And I believe that Kyle has already integrated Parsnip into one of the alert brokers. I believe it's currently working in Ample, and it's connected through to the ZTF data. So I believe these sorts of techniques that, because you can constrain the complexity of the model or the dimensionality of the model, then you can actually get reasonable fits from a small amount of observations. And so you can do these classifications quite early in terms of the supernova light curves. So I think there's a lot of potential there. And actually, I think it'd be quite interesting to see how well it performs with real observations, with the latest observations coming out of ZTF.
Okay, thank you. The next question was from William. He asked, my worry always is that the great Spark examples are single user examples, but how does it work for 5K astronomers? Do each need a Spark cluster, or perhaps we go back to the shared resource model, apply for time?
That is a really great question. And I think I noted and I didn't really get a chance to talk about this, but one of the real challenges is Spark and many of these tools don't really work in a multi-tenancy environment. They're assuming that you essentially have your own Spark cluster accessible to each individual astronomer. So we're not really sharing resources. I think this is something that we need to work on. And then I think this is one of the clear examples about where, if we can bring software engineering expertise within astronomy we can potentially adapt and modify these techniques, or these analysis frameworks, whether it's Spark or whether it's Ray or whether it's Dask. But to do that requires significant amounts of software engineering support. And this is why I think this is the place where, if we can identify what are the clear needs for each of these platforms, we might be able to bring some of the resources together to be able to actually bring engineering teams to actually address some of these questions.
Okay, I think we are out of time now. There's a second question from Michelle. If you can address that on Discord, that would be appreciated.
I'm very happy to do that. Thanks very much.
Okay, thank you. Can we thank the speaker one more time?